All right, let's get started. Let me make sure I'm live. Hey everyone, thanks for joining the delayed live stream. Sorry, the live stream got pushed back because I tweeted this out, but I'm not sure all of you saw it or not. Um, I'll have to repeat this again. I can hear myself. I don't have to repeat this. Sometimes I say things and then the live stream starts a bit late and then I have to repeat myself. I digress. I delayed this live stream because I didn't feel completely prepared for this particular live stream, specifically these three chapters. So I, for that reason, I just wanted to like be well prepared. I usually try to read three times or four times before doing a live stream, and this like these three chapters, this is me being critical of the book, but like these three chapters are like the basics of deep neural networks, right? Like if I'm sure most of you work in this field and you would recognize that fact, but the math in these is so dense. It took me like an incredible amount of time, and even then like there were some conflicting mentions in the text. So I'll rant for probably 60 more seconds and then we'll get to business. But like for example, in the phrase at one point they were applying Taylor series, they were applying Lagrange series. And I had studied those. I of course don't remember what that is, but you need to go back and look at that, and they just drop it like, oh, it's something you're supposed to know. And then later on at another point they say, oh, if you have a batch size more than 10,000, you should do this. And I'm like, what? I I have 8 GPUs, and even then, when I'm training models for some competitions, it's the batch size is not more than 30. So the math part especially took me a lot of time to digest. And my goal with these is, if you're new here, I'll just repeat myself. But the goal is to like give you a guided path of, hey, here's what to expect, or hey, here's a synopsis. And for that reason I had to like really think through for these chapters. So anyways, that's my rant, but we'll get started now. Sorry about that if you found that unpleasant, but I found the math to be somewhat difficult. I'm mathematically challenged. And one quick announcement, in Feb, or probably in 2 weeks from now, I'll be starting a study group for this book. So this is the book by Hugging Face team, and it specifically teaches you NLP stuff in Transformers and the Hugging Face API. So just stay subscribed. It'll again be free, and it'll just be a study group similar to this. With that, we can get started. So for the first 10 minutes, I'll give a summary of all the chapters, and then I'll share my screen and we'll go through the individual chapters, and I'll point out things that are worth remembering. The agenda is usually one chapter every week, but I felt I could do three in 1 week, which led me to delaying this live stream, and hence my rant. But we'll be learning about, broadly speaking, the basics of deep neural networks. That's how I classified these three chapters. So here are some notes, and to credit, all of these are just copy pasted text from the book. But here's a summary of what's a deep quote unquote feed forward neural network. And the authors say the goal of a feed forward neural network is to approximate some function f star, and f is the original function, or the function that is used to generate the data. Now one more thing, I'm just pointing these things out because I assume you will end up reading the chapter, or you just need a summary. But the authors say that, hey, we're trying to approximate how the data was generated. Realistically, that's almost impossible many times. So f star is the function that we're trying to approximate with all of this. And they say a feed forward network learns the value of best parameters theta. I'll later on also point out what theta is if you don't know that, to approximate the function. And they say we can also apply the neural network to a transformed input. So after this, they show you why XOR cannot be classified with the linear layer. And remember, deep neural networks are just linear layers in higher dimensions. So in 2D, that becomes a, sorry, in 3D, that becomes a plane, so sheet of paper. In higher dimension, it's hard to understand. So but basically that's what we're trying to create. And if you don't add an activation function, or if you don't add a non-linear transform, an activation function is a non-linear transform. If you don't add that, it's hard to approximate that. So that's what the authors spend mathematically proving in the next few paragraphs after this. um, But you can just assume that we can also apply this to a transformed input. So that's another discussion that happens. How to choose this mapping, and the mapping is referring to how do you transform this data. So they say one option is to have a generic mapping like an RBF kernel. Another one is to manually engineer this. And the authors claim that this was the pre-deep learning method. Realistically, the line is very blurred, right? Like this is a specific mathematical definition, but many times you'd end up also still transforming your data. So for example, there's a competition going on right now called RSNA, that works on mammographs where you're supposed to detect cancer. And let me quickly find that. So this is the Kaggle competition that I want to point out. But this contains mammographs of different sizes, right? Like one pre or one mapping changing you will end up doing is resizing the images. So the second point in the book is somewhat untrue. Many times you still end up applying some changes. Let's say you're trying to work with some OCR data sets where the documents are very have a lot of noise in them. So if you have scans that have a lot of noise in them, this is one of the problems that the H2 AI team is also tackling. So we have created apps called Document AI and KYC AI that are incredible with this. But for those cases, you would end up applying a lot of OpenCV transforms still, right? So the point I'm trying to get across is and you can find these on our website, so you can go to the H2A website and search for these. But the point is many times you still have to do some pre-processing, which is basically manual engineering of the mapping of the data set. So this is somewhat untrue, is what I'm trying to say. Or you can say deep learning learns phi function. If you don't know how phi is written, I'll again later on share my screen. But in this approach, we parameterize it, and the author says this can also be captured while learning. So the mapping that we do can also be captured by deep learning itself, is what they claim. I have spoken about this already, so I can skip this slide. But after this, they talk about XOR, the XOR example, and uh, a mathematical introduction to ReLU, how that works, and this show the proof that nonlinearity helps in deep neural networks converge. After this, they give different units that you can use for output. So if your output is expected to be Gaussian, you can use a linear unit. If it follows a Bernoulli output distribution, you can have a sigmoid unit. You can have a softmax or multinolly. After that unit, they talk about different hidden units. I'm just name dropping all of this because we have covered all of these in the previous live stream. So if you don't know what sigmoid or softmax is, or if you've forgotten, just look it up. It'll take a second to recall. And for me, I'm sharing my mathematically challenged brain, how that works. But I have to every time look up what a multinolly distribution is, or what a Bernoulli distribution is. I only know what a Gaussian and a normal distribution is. So those are the two ones I remember. They also talk about the different hidden units and transforms or activations you can apply. So they introduce ReLU, Reiki ReLU, TANH, hard TANH, and soft max. This was the summary of chapter 6, or the things I wanted to highlight. Now, from chapter 7, the chapter is about regularization. And the formal definition for that is any modification we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. Basically, you want a model that performs well in the real world. If you regularize them, they'll perform better. That's a simpler version of it. Most regularization strategies are based on regularizing estimators, and then there are a lot of mathematical definitions that follow in the book. The different types are parameter norm penalties. So for this, you add a penalty to the equation where you're calculating the loss function, and this is denoted as omega. Omega is simple to mention, so it's just like a headphone symbol. That's how I remember it. I'll again point it out later. There is L2 parameter regularization. We also get a different word introduction of it, Toko Honov. I will not remember it after this live stream, but they also name drop that, and it's also known as ridge regression. That's the authors introduced that. Uh, L1 regularization and norm penalties as constrained optimization. What is all of this? These are different types of regularization. Where are these useful? These help your model generalize better to the real world. How should you apply these? Realistically, it's just one function you usually call in PyTorch or in the nn dot module, and sorry, not in the nn dot module, in nn dot optimizer, or or the I don't remember the Keras module for this, but realistically, it's just one argument you end up passing. After this, they again give a thorough introduction to dataset augmentation. The simplified version of it is, if you can't gather more data, just augment your data ever so slightly and introduce some changes there or introduce some noise. So, for example, literally what I'm doing right now is resizing myself. So, this is me resizing myself to a corner. But you could, for images, flip them, resize them, rotate them, all the things. So, that also helps with regularization. They also talk about adding noise to different weights inside the network. So this is noise robustness, or how do you introduce that? They also introduce label smoothing and the mathematical definition of it, which is injecting noise at output targets. Semi-supervised learning is also introduced, which basically is using a trained model on unlabeled data and generating labels through that. After this, that's all for chapter 7 for highlights. So I'm just giving the highlights and then we'll go into the roots. For chapter 8, it's about optimizations. So first of all, they differentiate between learning and optimization. When are you optimizing a neural network and when are you trying to make it learn something? The empirical risk minimization formal definition is also introduced. They talk about a surrogate loss function. So many times the loss function you want to look at visually is not the correct one for the model, so you end up using a different loss function and then you end up looking at a different metric. Or for example, if you're presenting a model, you might train it with something else and then convert those numbers into a metric that is easier to represent, or you can just say, oh, it's this percent accurate or something like that. There is also an introduction to early stopping, and we look at the exact algorithm as well. In the book they have given the proper algorithms for all of these, but early stopping is helpful in preventing overfitting. So when your loss starts increasing after a few epochs, so it should decrease at least for the first few epochs, and after the ones that it starts increasing, you should stop the training. So that is early stopping. Why is it early? Because this might happen before the number of epochs that you want to train your model for. I've already come to homework, so I'll switch sharing my screen and share the book chapter. I just downloaded the PDF from the website, so it's the exact website that I'm using here. I'm curious in if anyone in the chat has read this chapters or any one of these chapters. I just want someone to share my pain and confirm that it was quite dense, or I wasn't just the person who found it very dense. Okay. I'll keep. Can I please share this URL? Aishwarya, this is deep learning book.org. This is from that. Just go to deeplearningbook.org. You haven't read any of the chapters. That's all right. You're still welcome to join these study groups. I'm just summarizing this stuff. So hopefully this should make it easier for you to read this. And at least for this book, or at least for this point onwards, you can continue regardless of the order. So before this, it's just other mathematical introduction, or you can watch the live streams independently as well. That's what I'm trying to say. Um, so now what I'll do is I'll point out specific paragraphs from the book that are worth highlighting. You can either just watch this video and skip the book. Ideally, you should also read it, or the best case, it can be a recap of everything, things I found important. Um, so as I pointed out earlier, the goal of a feed-forward network, according to the authors, is to approximate some function f star. A feed-forward network defines a mapping y is equal to function of x comma theta. So this is how you write theta if you don't know. Sorry. And it learns the value of parameters theta that result in a best function approximation. Why is it called feed forward network? Because there are no feedback connections in which the outputs are fed back into the model itself. We'll learn about this in chapter 10. They're called recurrent neural networks. Next, they tell you how this function can also be defined in another fashion. So you can think of every layer as a function, and this is how you can write it. So another side note, the reason why I'm pointing out all of these notations is the end goal I assume for everyone here is just to like have some help with digesting all this math. So when I point different things out, is just to like for myself as well to make a mental note, and hopefully for you to like remember different things. Different layers can be represented as f3, f2, f1, and these are different functions. So it could be whatever you're doing to the weights and whatever biases you're adding or whatever activation function you're applying there. The overall length is known as the depth of the model, and the final layer of this is known as the output layer. They also talk about the width of the model. Each hidden layer is typically is a vector, and the dimension of the hidden layer is the width of the model. Each element of the vector, so the vector that denotes the width, each element can be thought of as a neuron. They also talk about different units and how these can be denoted. This is how you write phi, by the way. So when I was saying the input can be transformed to phi, this is phi of x. So here they say phi is a nonlinear transform you can apply um, to the input. Three different ways that I highlighted earlier, just to recap. It's to use a generic phi, which could be an infinite dimensional phi used by kernel machines based on the RBF kernel. I don't think anyone uses this a lot today. Maybe they do, but not commonly. The other approach is to manually engineer phi, and they say with deep learning, phi can be learned, and it's just another parameterized approach that can be learned by a model. So after this, they introduce how can you learn the function XOR. So remember, we're trying to approximate F star. That's the goal of deep learning. Here, the goal is to learn or approximate XOR. So the authors introduce how to write these 4 points, and they also plot a graph for this. They remind you of the MSC loss function, which can be written like so. J denotes the cost function. And then they remind you how you can choose a linear model. And then they help you prove that a linear model just wouldn't work in this case. And the other simpler proof for that is I pointed out earlier, but linear models are just lines you're drawing, right? So if I pick up a pen here, there's no single line you can draw that will separate the one and zeros here. You can try this with pen and paper, but that's why this is an interesting introduction to non-linearities and also neural networks. But at least for the left figure, there's no single line you can draw that will separate the zeros and ones. So like if both the zeros were in two adjacent corners, it would have been possible. For this case, it's not possible. And that's why you need a non-linearity. And that's why a linear function wouldn't work. Um, they say we introduce a simple feed forward network with one hidden layer containing two units. Hidden layer is denoted, hidden units are denoted with H, and this is how the function is computed. So they write the weight, the input, and C, which is a constant. Later, they tell you how to write the second layer. Realistically, you never end up writing individual layers like so. They also tell you how to write this in different styles or like a graph. So this is an A. I think I'm forgetting the term, but I think it was a synchronous graph. I'm blanking out the term, so I don't want to mess up. But this is a graphical denotation of the model. So you can also draw it like so. And they introduce ReLU, which can be written like so. So anything or any value before zero becomes zero for this function, and after that it's literally equal to the input value. So it's the max of zero and the input. That's how you denote a ReLU, and you can the Python function is the same as well. So the authors prove that it's not possible to make this work with a linear solution, and then they denote ReLU and teach you how to use ReLU. So now the function becomes this equation 6.3 to be specific. So we've added a nonlinear transform where you're taking the maximum of zero and the hidden layer, or the value that is being passed through the hidden layer. So basically, you'd apply ReLU to the output of the first layer. Then the authors show how you can write that in a vectorized fashion. I'm skipping over this. You can read through it. It all makes sense. And basically, just by applying ReLU, you can approximate XOR. Someone's asking what is the best deep learning book you recommend? What is your end goal there? So for this study group, it's more to just like understand the mathematical definitions, and also like make it easy for us to read math heavy parts of research. But depends on your end goal. If your end goal is to like apply all of this or find the fastest way to apply all of this, the fast A book is the best in my opinion. After this, they talk about gradient based learning, and they say the non-linearity of a neural network causes most loss functions to become non-convex. This means that neural networks are usually trained by using iterative gradient based optimizers that drive the cost function to a very low value rather than linear equations solving this problem. They also point out that for feed forward network, it is important to initialize all weights to small random values. Uh, Practically speaking, you are either using pre-trained models that you are downloading through Hugging Face Hub, or you are using more complex initialization strategies. So after this, they introduce a few in chapter 7 or 8. Chiming her initialization is the most common one. And let me type that out in the chat. But if you look up in the PyTorch docs, or I am sure Keras has it as well, you can find different initializations that you can do for weights. Key is not to leave them as zero. So if you're like training a model from scratch, and if you're not using pre-trained values, just use a initialization function from the docs. Um, okay, moving on further, they introduced cost functions. Uh, Again, I highlighted this to point out how things are written mathematically, at least from the point of view of authors. So they say sometimes rather than predicting complete distribution over the target y, we predict some statistic of y conditioned on x. And they also define the parameterized model like so. So when you're trying to predict y using x and theta as the parameters, they talk about learning conditional distributions with maximum likelihood. So they introduce negative log likelihood as an energy function or a cost function, and then they refine it by applying some uh, optimizations or some constraints. They say in many cases, the activation function used to produce the output saturate, and the negative log likelihood helps to avoid this problem for many models. After this, they talk about learning conditional statistic. So they say we can design the cost function to have its minimum lie on the function that maps x to expected value of y. Solving an optimization problem with respect to a function requires calculus of variations, which is introduced in a later chapter. So it's not introduced in this chapter at least. Um, so now they apply like some derivations, but I just skipped over this. It's not necessary just to have it in your mind. So you can just read through what negative log likelihood is and why is it useful. That's all worth highlighting for me in this. After this, they talk about output units and how you can apply different transformations. So one win for me at least is when I see capital N here, I know instantly that it means normal distribution or Gaussian distribution. And these are the parameters being passed to that. So the authors then talk about for different, I think this was output units, yes. So for different expected output distributions, what kind of units should you have? So based on the output, how should you design the output units in a simplified fashion? So for if you just read through the topics, that would make sense, but they also define it very rigorously. Sigmoid units are used for Bernoulli distribution. And then they also remind you a Bernoulli distribution is defined by a single number. The neural network needs to predict only uh, p, where y is equal to 1 for x. For this number to be a valid probability, it must lie in the interval 0 or 1, between 0 and 1, both included. Then they define it mathematically, how you can satisfy this threshold. And a gradient of 0 is typically problematic because then the algorithm stops improving. So they define the sigmoid output like so. And this is sigma. This function here by cap is equal to sigma of W transpose H plus P. And then they introduce how you can basically calculate the sigmoid function. So this definition is not useful, but they're basically trying to prove the above point in the paragraph. I read through this definition. It's just reminding or trying to derive the above fact. So if you want to skip over this, you can. I just highlighted it because I was trying to understand it. And by the way, exp denotes e to the power. So p cap. This is not p cap, but p of y. I'll just call it p of y is equal to e to the power yz. That's what this denotes. Then they say the z variable defining such a distribution over binary variables is called a logit. The approach to predicting the probabilities in log space is natural to use with maximum log likelihood. Sorry, maximum likelihood learning, because the cost function used with maximum likelihood is negative log of the probability. Then they tell you how the likelihood learning of a Bernoulli distribution can be parameterized by a sigmoid. And that was for Bernoulli distribution. So after this, they introduced softmax units for multinolly and then they define the same mathematically here. I'm skipping over this because I gave the general idea earlier. Then they point out the fact that not all of these are very accurate. So you have different variations of all of these activations. So they say we may wish our model to predict a different amount of variance in y for different values of x. This is called a heteroscedastic. I, I'm going to butcher this, but this is what it's called. Neural networks, one more thing. I'm just pointing out different things that stood out to me. Neural networks with Gaussian mixtures as their output are often called mixture density networks. Now, for me, just again, like this is another side rant or side fact I want to point out. Like for me, at least before starting this study group, I would have just glanced over this equation and not read through it. But now I know that just reading through this, we predicting probability of y given x, and that is being summed over the range n, where we're using the normal distribution. So now I instantly recognize all of these different letters and what they're trying to denote. And usually in papers, sometimes you just need to read half of the uh, scripts to understand all of this. So that's what is important for me, at least as I keep working through this. And even though these are like very basic chapters in terms of deep learning, just knowing that okay, this is how you write sigmoid, so the zeta I pointed out earlier, or this is how you write softmax using a sigma, is what's relevant. All right, moving on further. Then they arrive to hidden units. So throughout this chapter, they're introducing different parts of a neural network. So far, we looked at inputs. We've looked at how the outputs changed. What are the different activation functions? Now we arrive to hidden units. And then they introduce ReLU and their generalization, why ReLUs really work, and how you can initialize this. They say ReLU units are typically used on top of an affine transformation, linear transformation. Then they introduce, sometimes this might not be the best approach to use. So you can have a leaky ReLU or p-ReLU. They also introduce logistic sigmoid and hyperbolic tangent, so tan h. And how is that denoted in the mathematical notation? Uh, I didn't highlight this earlier because it's a very straightforward read, and I'm just highlighting or summarizing different things. All right, continuing further, they talk about architecture design and universal approximation theorem. You can read through it, but what universal approximation theorem states is if you can create a extremely large model, it can learn everything, possibly. And this is somewhat true with GPT, but for GPT-4 to learn everything, it will probably take 49%. If I don't know if you got that joke, but these, realistically speaking, these models themselves are really expensive to train, right? And what you are looking for is how to make something existing work under a constraint for whatever business value you're trying to solve. So it's just a theoretical assumption, and it says that if you can create a very large model, it will work. Ayush is an expert in computer vision. I'll try to bring him on for the CNN part. He's learning deep learning and deep with Sanyam. Um, All right. So after this, they basically try to prove the point and how geometrically these things work. But that's all that's worth knowing in universal approximation theorem. They also point out the number of parameters in convolutional versus fully connected model. Normally, you would really don't use a fully connected model just by itself, right? So this comparison is only good for knowing theoretically, I would say. After this, they introduce backpropagation and the algorithm for it. So what I want to point out here is, and what I'll be pointing out here is how you should read these algorithms, and this is exactly how they're written in papers as well. For understanding this, I would say if you really want to understand backprop, first you can read through this, but the CS231N notes for backpropagation are the best place to learn and also practice the homework assignment where you end up implementing this. So if you want to implement it, I'll point out a link, but let's quickly go through this section. Varsha Bhatia says hello, hello. The input X provides the initial information that then propagates to the hidden units at each layer. This is forward propagation, or this is the forward pass. Backpropagation refers only to the method for computing the gradient, while another algorithm, such as stochastic gradient descent, is used to perform learning using this gradient. Um, One cool thing worth pointing out, the gradient we most often require is the gradient of the cost function with respect to the parameters. And this is known as delta theta j of theta. So j of theta is the cost function, and delta theta is calculating the gradient of the cost function. Aishwarya says he needs to read the book in order to try to keep up. That's the goal for this. So consider reading it. I'm sure it'll be helpful. This is just a summary, as I kept pointing out. After this, they talk about computational graph, and then they introduce chain rule of calculus. So I'll also highlight this in case you need a refresher. But let's say you have a function like so. So y maps to a function g, and then z maps to a function f. So to apply the chain rule, it works like so. To calculate the differential or the gradient of z with respect to x, you'll apply the chain rule like so. So you'll calculate the gradient of z with respect to y, and then y with respect to x. They also give you the partial versions of this. So this is del z by del x of I summed over all the elements. And if you're working with vectors, this can be written like so. So delta of z is written like so. And then they say delta y by delta x is the n by m Jacobian matrix of G. At this point, I don't remember what Jacobian is, and I had to look it up if it's helpful for you. So to recall, I was trying to refresh the chain rule for everyone, and this is relevant when you're trying to perform backprop. So you have to recursively apply the chain rule when you're trying to backprop, and they prove this point by showing a computational graph. So this denotes how the input goes to the output, and they then prove to you that hey, this is how you apply the chain rule. So to calculate or to backprop, you'll have to calculate the change of z with respect to w, and for that you can apply the chain rule like so, and then you end up denoting these functions. So f of y would have just been the mapping from x to y, but then the differentiation or the differential is written as f dash of y. That's how you denote it. After this, they start introducing the algorithms. So this one is a procedure that performs computation mapping to an output. This defines a computational graph where each node computes numerical value u by applying a function f to the set of arguments a. So for any loop, it's usually written like so. Here we're iterating over all of the elements where I is going from 1 to n, and you usually write do after writing for. So what we end up doing here is we store these value inside u of I, and then we iterate over all of the values from ni up until n, and then you apply a function like so. So you're calculating the probability and applying this function, and then again applying this function to a, which if we read above is the set of arguments that comprises the values of previous nodes. So then we apply this function to the previous node and store it in U again. So this is how the computational graph output is stored. All of this algorithm is the forward pass. So you're iterating over all of the values, you're storing them in a vector, and then you're basically doing the forward pass. And then you're returning this vector. Algorithm 6.2 is a simplified version of backprop, and then they use the gradient table. They introduce gradient table and use that to calculate or do backprop. And they also remind you how this can be written with partial differentiation. You can read through this. I'm not going to explain this in depth. For me, it took me a fair amount of time just to like read through all of these algorithms. But after this, they also point out the algorithm for backpropping through fully connected MLP. And again, not every paper does this. So not every paper points out inside a algorithm that, hey, you require this particular function or input. Usually it's just assumed, and sometimes they end up pointing out what it refers to. Aditya asks a very relevant question. How do you come up with complex neural network architecture to solve business problems? Do these theoretical concepts help you, or you just have to try things out? Realistically, you have a time constraint and you're reporting to a manager who's given you a deadline. So you could try these things, but what you're trying to do is like make things work as soon as possible. Of course, if you have the experience, you would know where to start. So depending on the particular problem, you would know where to start. Let's say you're trying to solve some satellite image problems. You would know what models work well with satellite images. So you would start there. And then once you reach a particular accuracy and then you can't improve, then maybe you'll rely to the theoretical concepts. Why are we as a group trying to go through all of this? When you reach the plateau and when you're trying to improve beyond a certain accuracy, or if you're competing on Kaggle and you're trying to improve, you end up reading a lot of papers. I look to my right because I always have a stack printed out. But when you're reading a paper, all of this appears there, and for me, it's very hard to read through. And as it turns out, this book at least helps with understanding all of that. So that's where this is really relevant. So after this, they give you the algorithm or the pseudo code. Many times it's called pseudo code for this. Now, the thing that I've achieved so far is I know that this is a dot product. I know delta, and I know how to read delta first of all, but delta of j basically means we're calculating gradients over the entire cost function. And this can be denoted like so. So that's what really helped, or that's what's the end goal of this study group. Aditya, again to answer your question. Surya is asking any Kaggle session in the future. Yes, tomorrow at the same time I'm doing a live stream. So I live stream for Kaggle stuff every Sunday. I think that's all I wanted to point out from this chapter. So if you haven't read, just read through the pseudo algorithm or the algorithms for back propagation. It at least took me a lot of time, a fair amount of time to understand. But the takeaways for this particular chapter were: hey, here's how you define your deep neural network. How do you define activation functions? How do you perform different functions on the output? What are the different calculus tricks that you apply when working with this? Can you please clarify the point about gradient descent? Does it find the local or global minimum? We'll just come to that in, I think, the eighth chapter. So if you could just wait for that. Uh, Ideally, you want to come to the global minimum. Realistically, you come to the nearest local minimum to the global minimum. So you try to optimize the error or the accuracy as much as you can. Marcos says hi. Hello, Marcos. So again, in my slides, I had pointed out regularization, and this is the official definition of it. Any modification we make to the learning algorithm to reduce its error, but not the training error. So the generalization error refers to the validation error. Is there any group that you can join for these discussions? Yes, absolutely. There's a community by H2AI which is intended for this. So you are welcome to join the forum here. And for the live stream, I try to keep it interactive. As you can see, you can just join these whenever I just live stream to this channel whenever I can. But you can sign up for this through this link. Introduce yourself. You'll find a lot of like-minded people there. But that's the goal for this community link. And of course, everyone from this group or anywhere is welcome. So if you know people that want to join a community, just send them to this link. Um, so that's the official definition of regularization. And then they say, in context of deep learning, most regularization strategies are based on regularizing estimators. Regularization of an estimator works by trading increased bias for reduced variance. I highlighted this because again, it for me, I had to recall what biases and what variances in this context. But generally, when you apply regularization, you're just adding one particular function to the training. So that's what you're doing. This is Omega. So I promised I'll point out Omega once it comes up. This headphone symbol, I'm laughing because it's not a headphone, but this is how you write Omega. Um, so this is how you denote parameter norm penalty. It's omega of theta to the objective function j. And basically, when you're training, you modify the cost function. So it becomes j tilde. You write a tilde symbol on top of it. And you just add alpha times omega function. Alpha is a hyperparameter that weighs the relative contribution of the norm penalty term, omega, with respect to j. When you set alpha to 0, that means you're doing no regularization. And if you set it to 1, basically, you're like being very strict. We typically choose to use a parameter norm penalty omega that penalizes only the weights of the affine transformation at each layer and leaves the biases unregularized. The biases typically require less data than weights to fit accurately. And each weight specifies how two variables interact. After this, they introduce L2 parameter regularization, and I had summarized this in the slide, so I'm going to mention a few things here. This is commonly known as weight decay, and if you want to generalize that, basically you're trying to reduce the weights or trying to bring them as close to origin as possible, and weights are usually in higher order dimensions. So they say this regularization strategy drives the weight closer to origin by adding omega, defined like so, to the objective function. This is known as ridge regression or Tikhonov regularization. Then they define how to mathematically write this. And again, worth remembering, delta is just calculating the gradient over a vector. So anytime you see delta, it's just calculating the differential of the entire vector. So for this case, it's with respect to the weights. And when you see this arrow, it basically shows an update. So here they write to take a single gradient step, they perform this update. So this means you update the weight like so, weight minus sigma of this term, and then that value gets assigned to weight. So all of this value then gets assigned to W, which is the weight vector. Written another way, then you can do some mathematical simplification, and they rewrite this in a different fashion. They say we can see that the addition of weight decay term has modified the learning rule to multiplicatively shrink the weight vector by a constant factor on each step. That's all I wanted to highlight for L2 regularization. You can again it for so like then they go into real mathematical depths, but I don't want to cover all of that. So for me, what I understood here was they apply some matrix decomposition which changes the Hessian matrix like so, and then you can simplify this to all of these values. Realistically, if you're applying L2 regularization, you just changing one simple hyperparameter. So that's all you need to know for this case. Then they show illustration of effect of L2 on the optimal value of W here, and how it transforms this particular how it transforms the optimal W. After this, they introduce L1 regularization, and it can be denoted like so. So omega of theta is the absolute value of W1, which takes the sum of absolute values of individual parameters. So basically add this term to the existing cost function with alpha. You can see that regularization contribution no longer scales linearly. Instead, it's a constant factor equal to the sine of W. So why is it sine of W? Because it says alpha sine of W. So this is L1 regularization. Another point worth remembering in comparison to L2, L1 results in a solution that is more sparse. Puranji is asking a question, so I'll pause to answer that. Is this book enough for mathematics for deep learning? This is quite dense for that. So there is literally a book called Mathematics of Machine Learning. Let me see if I can find that. Here you go. It is this link. Aditya pointed out E is epsilon. So thanks for that. This is mathematics for machine learning. You'll find this more concise. Um, This particular book covers more things than just the MML book. But if you want a faster paced um, solution, you can go to this link. Just look up mathematics for machine learning book. It should take you to that link. When they say the sparsity property induced by L1 has been used extensively as a feature selection mechanism. And they say this is used in lasso and different techniques. They point those out and also apply some more conversions. Then they talk about norm penalties as constrained optimization. So they introduce a cost function like so, and then they say again this is what I was ranting about. So if we wanted to constrain omega to be less than some constant, we could construct a generalized Lagrange function, but they haven't introduced this earlier. So um, take what you may, but you need to know what Lagrange is to understand this section. So here they talk about sorry, I blanked out. Here they talk about the constrained optimization for this approach. Again, it's just the mathematical definition, so I'll skip past it. After this, they talk about dataset augmentation, which I've also briefly introduced, and I think that was good enough. So I'm again skipping forward. They talk about injecting noise into the weights and into the outputs. So label smoothing regularizes a model based on softmax with k outputs by replacing the hard 0 and 1 targets with targets epsilon by k minus 1 and 1 minus e respectively. So this is how label smoothing works, and this is basically injecting noise at output. So that's what label smoothing does. Then they talk about semi-supervised learning, which I'm also going to skip. Nothing worth highlighting here. They talk about multitask learning. It's a way to improve generalization by pooling the examples, which can be seen as soft constraints imposed on parameters arising out of several tasks. They say, from the point of view of deep learning, the underlying prior belief is among the factors that explain variations observed in the data, some are shared across two or more tasks. Then they introduced early stopping and the exact algorithm for how you can use that. It is pretty straightforward, so I encourage you to at least read through 7.1, 2, and 3. It basically just stops training after you start overfitting. That's what it does. Then they talk about parameter tying and parameter sharing. So they claim that, hey, maybe you can reduce the memory footprint of different models. Um, they claim that convolutional neural networks do these. I'm skipping ahead if you don't know what they are, but if you do, they have kernels with fixed sizes that are again repeatedly applied. So, in a way, those parameters are shared. They say that might reduce the memory footprint, which is true, but that is what this section is referring to. So, parameter tying and parameter sharing might be helpful. After this, they introduce bagging and ensembling. So this is again very mathematically heavy, and I didn't find anything relevant here. Realistically, what is bagging? You have 10 models, let's say, and you have the outputs from them. To combine those outputs, you take all of those data frames. Let's say they are numerical accuracies of different things. You just add those and take the average. So what you've done is you've combined 10 models, and at the end of it, you'll have a bag of models that is more accurate than all of these models combined. Usually that's the case, and that is what is observed. So it's basically taking the average of all outputs. You could assign different weights. You could also do something fancy realistically on Kaggle. At least you have two-stage models. So the output of one particular model then becomes an input, and you have another model that sits on top of it, and it's a two-stage ensemble or stacking, as it's commonly known as on Kaggle. Then dropout is introduced again. In a very simplified fashion, what it does, it deletes some of these connections randomly, or it deletes some of these values randomly. So you could set dropout from 0 until 1, where it could be 100% or 0%. What it's really doing is it's removing some connection randomly, and this helps reduce overfitting, because maybe this particular connection was getting overfit. So by randomly deleting that, you could help your model generalize better. Again, it's regularization. That's the name of this chapter. So we're learning all of these techniques. Okay, I am just scrolling further to see if there's anything else. I think that's all for this chapter. They talk about adversarial training in a lot of dense fashion, but again, nothing worth highlighting there. I wanted to cover optimization as well today, but we're almost over the hour mark, and this chapter would also take me a significant amount of time. So what I'll do is I'll wrap up here, and we'll continue from this point in the next live stream. I'll also change the title later on because we didn't end up going through this. So for the next live stream, I am aiming at chapter 8 and 9, which is optimization and CNNs. And let me suggest some homework again quickly for everyone. The homework suggested is to read through chapter 6 and 8. You can read through CS 231 and notes for understanding backpropagation. And let me see if I can take everyone to that. This is the CS 231 and notes. But they have a fantastic module on backpropagation. And then Sebastian Ruder had written a very nice piece on different optimization techniques. This was a while ago. So let me see if I can find that quickly. Optimization for deep learning in 2017. He introduces all of these different techniques that might be relevant, but we'll be going through that next week. So I haven't covered chapter 8, but if you end up reading chapter 8 and you want a fantastic extra read, go to ruder.io and find his blog on this particular topic. Um, I'd also promised that I'm working on notebooks to convert all of these lessons into Pythonic code. That's still a work in progress. I'm still trying to figure out how to best do it for these chapters. If you have any ideas, you're welcome to share a PR. That's the first link in the description if you want to send a pull request to it. Or you can simply just subscribe and we'll again meet next week. So these are the suggested homework. Consider reading these chapters, and I'd only suggest 2 extra resources if you want. For next week, we will be reading chapter 8 and 9, and I'll probably wrap up around 10. So we'll probably meet for 2 more live streams, and after that, I'll be starting the study group for this book. So again, I mentioned it towards the start, but I'll be starting a study group for this book sometime in Feb, probably in the first week of Feb. So thanks everyone for joining. I'll see you next week. We'll read the next 2 chapters in.